This idea is actually fine. What we want to just state here is that the reciprocal of the derivative is a thing. So basically, if you have, let's do this with an example, x is equal to 2y squared, you could, of course, rearrange and make y the subject. So y equals like x over 2 square rooted. And you could like differentiate that in that form. However, if you thought this was easier to differentiate and do dx dy, just swap the letters you're differentiating round. This isn't implicit. This is just they've become the opposite of each other. Like I'm now saying x with respect to y. This would literally become 4y. Do we see if I make this the derivative like operator, I'm differentiating y terms. So that's what you would get. Now, if you then looked at what dy dx is, and you said, well, that's 1 over that. This is just to justify to you that it works. 1 over 4y. Well, that would equal to 1 over 4, which is the same thing you would have got if you differentiated this. Okay, but you can, what we're saying is you can do it an easier route if you recognize that a derivative can be treated as a reciprocal, you can differentiate the other way around. So this is getting the derivative in terms of y. You could still put it back in terms of x using that substitution. But what we're saying is if you differentiate the other way and then flip it, the net effect is you've still found the same derivative. You might have just found it in the other letter, which you'd have to sub in for. So that's just a point to make that you can do that. What we'll do this bigger question now together. So let's look at the key bits here. So we've got a conical funnel. So the shape is important, especially with these formulae, because the question involves rates of change. So we're probably going to this idea of the chain rule. And it says the water flows out of a conical funnel at a rate proportional to the square root of the volume V. Determine an equation to model the rate of change of the depth of the tank H in terms of H and any other constant terms. The volume of the water in the conical funnel is given by V equals pi H cubed over 12. Right, there's a lot going on here. A lot of people don't like starting questions like this, but let's see how we go. So we're going to expect answer to contain these variables because it says in terms of H, so that's what they're looking for. It's 4 marks. I'm going to give you 2 minutes as a bit of a head start on this, and then we'll go through this together, but this is all good. Let's give it a try. Yeah, guys, do look out for the fact that it says water flows out of the conical funnel. So we're losing the water. So the gradient, this is where the derivatives are actually a minus. Okay, so this is maybe a type of problem you've practiced, but it's something we're going to have a little look at now before getting on to some harder derivatives. Okay, so I'll give you another minute or so, maybe 40 seconds, and then we'll start working through this together. That's great. It's a good follow-up. It's probably feels harder than what we just did. We'll start having a little look in a minute together. So another 15 seconds or so, I'll start going through it. Here we go. So these are like the derivatives this question is going to involve, dVdH and dVdt, because ultimately we wanted dH/dt. So if you've kind of put that as a side note somewhere, well done. Might be worth making a little note of, because that informs us of what derivatives we actually have and what one they might have already given us already. So they have actually already told us that dVdt is proportional to the square root of the volume that's in there. Now, we also know it's flowing out. So the amount that's like flowing out is proportional. This is negative. This is a potential trip hazard in the exams because it's flowing out, it's minus, the derivative is getting less. So it's decreasing. So that constant will need to be negative. Now, that's what we've got at this stage. So to go from a proportional to an equation, we have to put a scale factor, constant of proportionality. So dH/dV, we actually need the volume of the cone, which they gave us. They gave us the volume here, but they've given us something there. They've gifted us something that we can actually differentiate. And if you did that derivative, you would be finding dVdH. So times by the power, drop the power by 1. dVdH would be equal to pi over 4 h squared if you tidied it all up, because you'd have 3 pi h squared over 12, which would tidy up to pi over 4 h squared. So you've differentiated the volume. And that is typical what they'll ask. They'll tell you a derivative in words. They'll tell you a formula to differentiate. Then we've got to combine them. So combining that, we want to do this combination. And annoyingly, this wants dH/dV for it to cancel out in the right way. And we had dVdH. So effectively, we've got to flip it. We've got to do the reciprocal. So instead of pi h squared over 4, it's like 4 over pi h squared. And that was dVdt. So putting it all together, we are going to times the two things. And that's where we're at. Okay. So let's have a little check. So dH/dt will be dH/dV, which we've just worked out, times minus k lots of dV/dt. Remember, dV/dt was the root proportional to root v, which we've put in. And then tidy that all up, and we get to this stage here, and just further tidy it up if you can. Okay, so I know we've gone through that relatively quickly. I'd say this bit, don't let that put you off. That's also where we replaced v in the root with the actual volume they gave us. And then it is just tidying it up a bit, leaving the answer in terms of k, which they did ask for. Okay,